Okay, folks, we are going to move on to module number 11 and discuss frame buffers. And this is going to be our last lecture on modern OpenGL before we move on to ray tracing. So it's an exciting one. We're getting into some advanced stuff, as we've been finding with the normal mapping assignment and so on. But it's something I wanted to share with you for our warm-up for today is this nice YouTube channel. It's called 2-Minute Papers. They focus a lot on doing graphics work, more recently sort of artificial intelligence papers, but you can take a look at some of these topics that are kind of fun. Baking and melting chocolate simulations, for instance. Virtual characters, teaching them how to walk and generating different artificial intelligent models. So there's a lot of really nice content on this YouTube channel, so I just wanted to share that to you as a fun resource to continue looking at what's possible in computer graphics these days. Okay, so with that in mind, let's begin. Last lecture we were talking about the scene graph data structure. So that is the picture in the top right here with the hierarchical structure as a way to organize your scene. And this could be used for many purposes. It's mainly used for organizing our scene, making complicated transformations more reasonable, but can also be used for things like optimizations. And then we talked about terrains and height fields. So for instance, using a triangle strip to more efficiently render a terrain. And then we talked about this height mapping technique where you could use a height map texture to lay over the terrain to set the height values. And then we proceeded to put a color map over the terrain as well. Okay, so just some logistics. Assignment number 5 is due shortly. Again, there's 2 tracks for this assignment. Option 1, just getting the brick wall working. That's just working on the shader for up to 95%. And for those who go above and beyond, integrating the normal mapping into your object loader. Now, the normal map, you'll know if it's working if it looks really good on the brick wall. On the object models, you'll know it's working if the texture is a little bit shimmering, I suppose. The bump map isn't giving a lot of depth in the models provided, but you'll know it works if there's a little bit of specular highlights. Okay, and I'm also going to push assignment 6, which is going to be on the scene graph. It's a relatively short assignment, but will give you some exposure to scene graphs and how to work on them. Okay, so otherwise just keep working on your final projects, which will be due on the last day of class, posted on the website. And then we'll have a few labs and maybe one more assignment. I haven't decided yet, but they'll tend to be a little bit shorter for the remainder of the semester, so you can work on your final project. Okay, so today we are talking about frame buffers. So again, we're sort of getting into the advanced OpenGL section if you're following along in learnopengl.com of contents. And if you remember, buffers were one of the great ideas for how we do things in computer graphics. We put data into buffers and are able to ship them over to the GPU where they can be processed, and then we write these shader programs to actually manipulate the information for our machines. Okay, so let's talk a little bit about buffers. So buffers in general, again, we've looked at a couple different ones in this class. Vertex buffer objects, where we store our geometry data, and then of course index buffer objects for a more efficient way to access that data. So we're able to sort of select which vertices to use in our vertex buffer. And of course our vertex buffer can contain other information such as color, texture coordinates, the normals, and so on. Okay. But now, we've been focusing a bit on buffers, but there's also another type or class of them, which is the screen buffer. So it's just another place where we can store data. And we have been using these a little bit behind the scenes. If you recall, we have something called the color buffer. This is just where we draw our final colors to. This is what our final, our frag color in the GLSL shaders has been drawing to, particularly there. We have something called the depth buffer, which performs the depth test and ignores the fragments that we don't see. So this was our Z buffer, again, that sort of grayscale image showing how close or far away things are to the camera. And something we didn't cover, but it's another type of screen buffer, is the stencil buffer, which controls which fragments are drawn. So a stencil is a way to sort of mask away certain details. And this can be helpful if you only want to show part of the scene, for instance. Okay, so just to make these sort of clear, again, color buffer has our actual color here, this image on the left, and then the depth buffer is again showing us which fragments are closer. So the darker colored fragments, the more black colored pixels versus are much closer, versus the further away pixels, the whiter they are, the further away they are. It's just using color again to convey distance. Okay, so on the left again is the color buffer, and the right is the depth buffer. Okay, stencil buffer, just to give you an idea of what this is again, is which fragments to omit. So here is a scene with some cubes that you're walking around, and then here's your actual screen buffer. So this is sort of overlaid over the image, and anywhere there's a 0, we do not render. Anywhere there is a 1, we do render. So here's an example after sort of overlaying this mask and displaying what's in our actual stencil buffer. And this tends to be useful for things like reflections, mirrors, and those kind of things, where you only want to show part of the scene where the mirror is reflecting. Okay, so my question is, though, with these different screen buffers, we want to look at, what is the actual mechanism for storing these buffers? Okay, so again, screen buffer, well, they're just drawing some data. And the data that they're drawing is just an array of pixels. It's just, however big your screen is, the resolution. That's the information that's drawn to the screen. Okay, and the composition of those different buffers is what ends up drawing your final frame. Okay, so now my comment is, wouldn't it be nice if we actually had access to and could modify these different buffers? Then if we can modify those buffers, maybe we can control how our final scene looks and do some cool post-processing effects, or even just debug what's going on. And the good news is, as you can imagine, this whole lecture is we can do this. So this is actually really cool. SDL, for instance, gives us by default a color buffer that we've been drawing to, but we all along have had control of this buffer. Okay, so I want to talk about frame buffer objects now. Okay, so this is going to be one of our screen buffers that we can use. And again, OpenGL, right, it's a fairly low-level application programming interface, so it allows us to create our own buffers. These are known as frame buffer objects, or FBOs, as they're sometimes abbreviated, and they just are a container that can hold several screen buffers. Okay. And what's cool again is that we can draw whatever we want to these buffers, and then we access the frame buffer at the very end of our graphics pipeline and draw things. So here's our sort of pipeline. We have some data loaded from the CPU, maybe loading up some object models or something, those .obj models to be processed and rendered and so on. Then we have OpenGL here. Here's our API, which is going to process this data. We build our graphics pipeline with our vertex shader and our fragment shader. And then at the very end, when our fragment shader says, hey, here's the colors going into our color buffer, which we have by default, and our depth buffer to figure out what to draw and what to sort of clip away from the scene. For stuff that's too far away, we have the frame buffer, which is the final part of our graphics pipeline here. Okay, and then this, since we get access to it, we can change the appearance if we want at the very final step. Okay, so a nice way to illustrate this actually is by doing a little graphics study. So this is sort of going to be showing how to compose different buffers to a final set of images to create one final, what I'll say is cooler or neater image effect. Okay. So again, here's just the modern OpenGL pipeline, which we just saw in a second, but here's just another look at it. If we like vertices, then we start our data, send all this information to our vertex shaders, we figure out how to fill those pieces in, then we run the fragment shader, then we figure out how to color those pieces, There might be additional steps like blending and so on, and then of course here it is on the frame buffer. Okay, so back to the graphics study. There's a nice blog here by Adrian Kraj, who does these sort of graphic studies. So I just picked one sort of at random. There's a bunch of different games. You can pick your favorite. Doom's kind of a classic game I'll use for this instance that shows some neat effects. And anyway, I'm going to show how they sort of compose one frame in this game. Okay. Mind you, Doom's a little bit of a scary game, so if you want, you can fast forward it, or look at other examples. But I think this is a really nice one. So that's just your heads up warning. If you're not into action games, again, there's a bunch of other examples on the site. First question is, where does the color come from when we're trying to draw a frame in a game? A game or movie sometimes, but more typical of games, this is how the information is stored. In games, we just load up usually one really big albedo texture or our diffuse texture into a really big image. Okay, so this is 16K by 8K, so really, really big image with all the texture data. So this is sort of zooming in on different parts that would be covered, part of a wall here, part of another wall and a creature, part of the map or whatever. If you zoom in really close, you can see all the textures that are used in the game. Okay, they call these mega textures. They're nice because you allocate the memory just once, and then that's all you have to worry about. As long as your graphics card can store whatever 16 by 8000 is. And there's apparently 128 sort of pages of these, so quite a few textures, but they're all compressed into this one image. Okay, and then additionally, you might have other information that you want. We talked about this briefly with light maps, where you could sort of bake in the lighting. So that could be something that's pre-computed, but you're likely computing this in real time as well. And in this particular version, they are doing something, they're computing the depth map to help simulate some lighting computations and where shadows are, for instance. Okay, so this particular image is calculated every frame. Okay, and then they use something else called a velocity map, and this is kind of an interesting idea with some information you can store. So, for instance, here's your character here, you've got your weapon or whatever, and you're moving through the world, and then this creature comes from the left side, I suppose, and jumps out at you to scare you. And what this image is showing is a similar technique to the normal maps, where the direction that this character is moving, so sort of to the right here, we're coloring in the vectors where this motion happened in a particular direction. This gives you something called a velocity map. And you can use this to sort of create a blurring effect based off of where a character's moving. This is something called motion blur. It's something we experience if you turn your head really fast a bunch of times. Things will kind of get a little bit blurry, and this just gives a sort of nice touch of realism in the game. Okay, here's the depth map again, just showing how this scene looks. Again, objects that are closer are darker colored pixels, and objects farther away are lighter colored. And again, this is calculated every frame. So every frame we have this velocity map, we have our depth map, and then we have other things that we might have as well. So for example, our normal map, which we've talked about, is computed. These normal maps have been created by an artist, so here's just one rendering of it. And then we might also have a specular map. Again, a specular map, lighter colored pixels are things that have high specular components, so they reflect a lot of light as opposed to darker colored things. So this gives a more reflective surface, and this is more of a plain, like matte surface. If you've ever painted your room and chosen paint colors, or if you look at your office desk, if it's reflecting a lot of light, it's probably a very, maybe it's a metal desk or something versus a wooden desk, which would reflect less. So again, that's just what the specular map is highlighting. Okay, anyway, so we've got a bunch of these different maps all computed every frame in the game. And the game's running at about 60 frames per second, so this is a lot of information, but our GPUs can do it. Okay, so again, there's this trend here where I have all these different frames calculated, all these different maps calculated per frame, and they're stored in some buffer off screen, right? I'm actually showing you this buffer here, this velocity map, this depth map, this normal map here. So these are all in a separate buffer somewhere, right? We have all these pixels where we can access. So again, one of the takeaways here is there's more than just color that makes up the final scene, which is really cool. And then the second is, if we compose these in a certain way, we can generate a cooler image for us to view. Okay, so let's go back to frame buffers. Okay, so our idea is we have a bunch of these maps, textures, if you will, if you want to refer to them that way, but just maps of pixels that are computed every frame, and they're stored in buffers. So let's look at the OpenGL frame buffer. Okay, so now our goal is to figure out, how can we render, how do we as programmers actually render this information into a separate texture? Okay, then you can access the texture and do all kinds of cool post-processing things if you want to create your own velocity maps or, a motion blur effect or, grayscale image or something like that. You can play around with that, okay? Because once you have that data, then you just, it's a texture, and then you can manipulate it in your fragment shader. Okay, oh yeah, here's just a little warning, we're getting into a territory where I think a lot of the internet tutorials sort of break down. The learnopengl.com one's still pretty good, but that would be the one to look at alongside this lecture, and it's the one that's linked in our module. But otherwise, I haven't at least at this time found other good ones. So hopefully this is a nice framework on actually implementing these things. Okay, but the nice thing is, as we've gotten more familiar with OpenGL, the ideas about creating buffers are all relatively consistent, right? And that's the sign of a good application programming interface, this consistency. So what we're going to do to create a frame buffer is generate a frame buffer. We're going to bind to it when we want to use it, and then we'll delete it when we're done with it. Okay, just those 3 steps here. Okay. But when we're binding to the frame buffer, we're going to squeeze in a few other steps here that are new, because we need to actually create a texture. So in this step, instead of when we're doing our vertex buffer object, we're doing something with generating vertex information. So we had these buffers that we had to fill up. This time we need to actually fill a texture with some information. And we're actually also going to do something that's going to be a little bit weird or feel like magic, but we're going to draw a single quad, which we're going to overlay over the screen. So from now on, we're not even going to draw our geometry out to the scene. We're just going to draw into a texture and then render that texture on top of a quad. Okay, so that's what's going to be going on here. Okay, so here's our frame buffer abstraction. This is included with your lab today, but I want to just talk about it with you so you know what you're looking at. So this is a new type of object that we have, and let's look at the different pieces. The first thing I want to show, probably the most important in our first time, I believe, of doing this, is that this frame buffer is going to have another shader. So we're going to have another set of shaders here. So previously in our shaders folder, we've had frag.glsl and vert.glsl. We're going to add our frame buffer object fragment shader and our vertex, or it's going to be frame buffer object, or FBO vert.glsl. Okay, so totally different pipeline in a sense of what this frame buffer is using. It's going to select and bind that GL program, which is our set of shaders, to render things. Okay. Okay, and then there's sort of just this note of +1 for good abstraction, right? If you remember, we abstracted the shader class into its own component here. So again, just a plug for object-oriented programming. When it works nicely, it works nicely. Okay, so our constructor here is to, for our frame buffer object, do a few things. One, it's to create the shader and load the appropriate shaders. Okay, there's these frame buffer object vertex shader and frame buffer object fragment shader that I talked about again. So we're creating our own pipeline here. So it's going to use these different shaders than how we're rendering our geometry, for instance. Okay, and then we're going to set up our quad here. Okay, so you can look at this actual function, but this is just going to set up a vertex buffer for, way back to lab, when did we start modern OpenGL? 4 or 5, where we're just rendering a triangle and a quad here. That's all this function's doing. Okay, and then we have a separate function for creating our frame buffer. Again, it's going to look similar. It's just the width and the height of our screen, but this is where I said we have to do just a little bit more work in our frame buffer because, well, a frame buffer contains a bunch of pixels that have the actual thing that we want to render, so we need to generate a texture for that. Okay, so we're going to create our buffer. We do that with the gen buffer function. We bind to it, so again we're selecting or saying, hey, OpenGL, we're working with this. Remember, bind is like select. And then we immediately generate another texture. So we're going to generate our texture here, and then bind, select this texture that we're working with, set up some parameters for the texture, and then we have this function GL frame buffer texture 2D, which for our frame buffer that we're using binds to our this texture that we're using, our color buffer, to the currently selected frame buffer. Okay, so that's what we're actually drawing to now. This texture, they're sort of linked together in this way. Okay, and then here's the rest of the setup where we actually create our render buffer object here. Okay. Okay, so this step's a little bit. There's one other buffer, this render buffer object. In the next slide, I'll go between the differences. But basically, what this is doing is creating something that we can put a bunch of bytes into that are just pixels. So whatever information that we are drawing here, the actual texture, its width and its height, which is stored here. And then again, so we've selected this frame buffer here, and then we're sort of tying it to this render buffer here, which actually does the drawing to our screen. So the frame buffer is just a texture that we're drawing to. And then we're going to take this frame and put it into our render buffer. Okay, so just maybe another aside, render buffer versus frame buffer, they seem like they should be the same things, but render buffer is really just a bucket of bytes where we store image data that OpenGL understands, so like a texture or something that we don't draw to the screen, and then the frame buffer is the actual thing that we're drawing a texture on, okay? And it's the last stage in the rendering pipeline, okay? So that's our setup in the frame buffer abstraction here. So where can we actually use it? So included, we've added another renderer abstraction that contains all of our information needed to render our scene. And this is really our master class. This is what we've been building up to for the entire term in OpenGL. This could be your starting point for the final project, or if you decide to take things further. But the renderer now stores our frame buffer. Okay, so just looking at other things in the renderer class, I think it's kind of neat. It stores our camera, so we just have one camera per renderer. My little to-do note is that I don't necessarily need to make this public, but it is for now for ease. It contains the root of our scene graph, and then it stores the projection matrix for our camera. And then we can render and update the scene and so forth. Okay, so this is our render abstraction, the final abstraction, tying everything together. Okay, so in our render function, we actually have to update our frame buffer. Okay, so we update our frame buffer, and then we select it in our render function. So we update, whatever work we need to do when we update, which is typically just binding to it. And then when we bind to anything in our shader, or whatever shader we're bound to, that's our chance to then again set any uniforms or do any work that we need to. Okay, so for instance, we might set some values here. Okay. Okay, so within our render function, nothing here has actually really changed, which is actually really cool because all of this stuff that we're doing here, enabling things and setting up the viewport, clear color, maybe rendering in polygon mode, and then finally drawing our scene, this stuff's all the same. The only stuff that's really changed is now we're using this frame buffer here. We're updating it, binding to the texture that we're going to draw, and then when we're finished, we just unbind with it. Okay? Okay, so the magic step actually occurs, though. I said there'd be a little bit of magic here when we are finished with our frame buffer. Okay, so again, the rendering stage here, we update our frame buffer, select it, and then here again, we're just doing our normal drawing the geometry, all the normal stuff here. But then when we're finished with our frame buffer and unbind from it, here's what we do that's a little bit strange. So we unbind, and then we disable the depth test. We don't need depth because we're only going to be drawing a 2D image on our screen. Okay, we set our clear color to whatever we want, so we clear it. And then what we do is we bind to our frame buffers shader here, and then we draw the frame buffer, this quad, over our screen here. And then that's what will actually show our scene. We're just drawing, again, a quad over our screen with the 2D texture. Okay, so we render our scene like normal here to our frame buffer. That's because it's been selected. And then we just disable all of our 3D graphics, then just draw our 2D quad on the screen. Okay, so what you get when you run this is the terrain from last week. Okay, so it's going to look exactly the same. You're going to say, hey, what did we do? We created some abstractions. It looks the same, at least to the user, but we'll know it's actually done to the framework. And to really know that it's been done with our frame buffer, or frame buffer framework here, you can actually set the wireframe mode, so something we've sort of been doing, to just draw the lines. And then when you're actually rendering the scene, if you toggle between this, you'll just see a quad, so 2 triangles drawn on top of the screen. Okay, it won't have the texture because you're drawing in wireframe, but that's pretty cool. So everything got accumulated, all the actual image data got drawn to our frame buffer now that we're in control of, and laid out on top of this scene here. Okay, so that's pretty cool. Think about that. Let that sit with you for a few moments. Look through the code, read through the learnopenGL.com, but understand, by doing this, again, just drawing everything to a texture, this is how we can get these same kind of cool effects. If I go back to our graphic study of having different maps by drawing those each to different frame buffers or different textures, and then laying them out as we would like. Okay. So let me give you some more examples of how frame buffers might be used in practice as well. So something that's cool is doing selection with frame buffers. So I'll mute this here. But the basic idea is you have your object here, and you can select what they're doing here. Let me see if I can pause it in time. You can basically, this scene is made up of a bunch of quads here, sort of like our terrain, but by coloring them different colors here, maybe a darker red, lighter red, a bunch of unique colors. If I move my mouse here and figure out what color pixel is under the mouse, that's a way I can select this region if I want to do selection. So this is something, this is one way to select objects in a OpenGL scene. So you can see how we're able to just select this one region. There's a unique color in our frame buffer that we're actually detecting under the mouse, and then we can highlight it in our 3D scene. Okay, so it's a really great way to, or one of the ways at least, to do object selection in OpenGL. The other very cool thing is to do debugging with your frame buffer object if you just want to see, for instance, if your geometry is there or not there, or how it's looking. This is a nice example, again, similar to the graphics study we were just doing, where we can see the different passes in our renderer. Okay, so this is just an outline here, so sort of doing some edge detection. The colors, here's the with the shadow map, and here's the depth information. So it's kind of cool to see these. I'll let this one play so you can just see the different techniques: edge detection, real-time shadows in this pass, and left just the color. Okay. Let's see. Oh, and then rendering scenes to texture. Again, if you want to do something like create a mirror effect, or the frame buffer object is stored in a texture, so I can take this scene here, and then if I have a piece of geometry here, this quad here, I can actually just render what I'm looking at, or part of what I'm looking at, to a texture, and that's a way to create a mirror effect. Okay, so super powerful technique here that can be used. Okay. But what I want to get to you, or move us towards, is actually the fun part here. This is what you're going to be moving or programming in the lab, is this idea of post-processing effects that you can do in your frame buffer object. Okay, so post-processing, when I typically hear of this term, I think of it as, you've taken a photo, on your camera or your cell phone or whatever, and then you're using Photoshop or some image editing program to touch up the image to make it look better or create a different effect. Okay, so where we're actually going to be doing our touch up is in real time and in the fragment shader. Okay, so we don't do a lot of 2D processing stuff, but now's your chance to do a little bit of image post-processing. So there's actually a lot of nice examples on learnopengl.com that show some of these examples. So for instance, because we've drawn our entire screen to a texture, again, we have that texture in our fragment shader, and we can modify it. So in this case, in this example, they're inverting all the colors by subtracting 1 from the color, and that flips all the colors. Okay, so this is an example of one post-processing effect you can create. Now there's many different post-processing kernels that you can apply that create other particularly interesting or neat effects. So I'm calling these programs that you're going to write in your fragment shader kernels, but they also go by another name known as a convolution matrix. So you can look at some examples here. And the basic idea is, let's just look at this one, the identity. Per fragment, or per pixel if you want to think about it this way, I'm going to give it the original color here, just a 1. Okay, and that'll return you the same image. But if in your fragment shader, if you look at, say, assign some different weights here and color something the opposite color here, this is a way to get a edge detection. Okay, so I'm sort of weighing, this image here, or affecting my 8 other neighbors. So I'm figuring out by passing in or using this kernel, I can get a sort of sharper edge along this shape. Some other examples are if you just take the original pixel and then sort of multiply or normalize it, you can create a blurring effect. Okay, so these will be some different kernels that you can play around with and implement in your actual fragment shader. Okay, so just looking at the Wikipedia page is still a little bit obscure, so let's look at it in sort of learnopengl.com. They have a nice example of the blur kernel. So this is the kernel that they're applying to this image, and you can tell it's a little bit more grainy or blurry, right? You could use this for a motion blur effect to give, again, if the camera swivels really fast, apply this sort of blurring effect. Okay, so your lab task is to modify just the fbofrag.glsl to create this sort of nice post-processing effect. Okay, so here's an example from learnopengl.com. You're going to have to adapt this to our code base. In fact, you can use any of the post-processing effects, edge detection, blur, maybe something more interesting than the invert, but just apply one of these post-processing effects to our scene to get something new, okay? So just looking at this is the idea of the kernel here that you can, is proven to work. Here's your sort of taking samples from your texture here, and then you're just, whatever that texture is that you're reading from here, you're just looking at the offsets from that actual fragment that we're looking at here and getting some weighting to discover what the final color would be, okay? And that's how it works. Okay, so before we close, I just want to give a few notes here on our sort of rendering study, because we've sort of made it to the end here of our abstraction with this renderer here. And we're getting, we're well after the point, actually, I should say, where it's nice to have this abstraction in this sort of separate renderer class, for instance. And we really do need to think about what good abstraction is. This will be something I want you to think about as a takeaway of this course, because we've been sort of slowly building up this bigger and bigger project, even with your model loaders, for example. It's a sort of slow build up one after the other. It's quite nice to build something big, but as things get bigger, you want to think about the abstraction and your API and how you'll use it further. So one of the questions I ask is always related to sort of performance, because that's something I care about, is, is what we did any faster than just rendering like we normally did, okay? And the answer is, probably not. And we might have even added some slight overhead by, drawing things to a separate buffer and then a quad before finally drawing. Now, this is what OpenGL ends up doing anyway, so maybe it's the same. Maybe we should just be using one of OpenGL's, the color buffer that it's already created for us in SDL, and just draw to that. But we've only added a little bit of overhead. So then the question is, hey, if we've slowed things down, why even bother with this approach? And the answer is, sometimes we just have to. In the case of the Doom example, we might want to aggregate multiple screen buffers together to create a more complex and better scene. We can't do it any other way. So that's why OpenGL gives us this functionality, again, to render different pieces of data to different buffers, which we can aggregate for the final picture. Okay, so that's just thinking about our render. Now, if we were in class, so apologies, we're in the online world, but I still want to give you this exercise. We won't divide up into groups at all. But something I would like you to just spend a few minutes time doing is to look at different rendering engines. Excuse me. So here's a list of different, sort of professional grade graphics engines here that you could look at, and just spend a few minutes doing it. I've sort of linked some of the links to how the rendering pipeline is built. Normally we would, again, present these in class, but if you want to post on Piazza for fun, you can do that. But it is nice to just sometimes dive into some source code of some of these things or read a little bit about their documentation architecture. at the least, you have this if you want to revisit it later, just to see again how modern engines are implemented, the different things folks are thinking about. Okay, and just to guide, you can kind of think again, which engine did you look at, and try to pick out, what were the key ideas. Did the authors discuss the trade-offs? Do they know what's good and bad? Can you kind of tell what they're trying to optimize for? You know enough graphics that it's worth looking at this stuff at least for a first time, and then by osmosis, sort of gaining some more knowledge. Okay, so there's some more information here. There's even a thesis about game engine design that's kind of cool. There's some other YouTube videos and so on. Okay, so with that, go ahead and complete the in-class activity. This is a shorter lecture, so hopefully you took a break if you needed, but we are wrapping up. And again, just your task is to perform some sort of post-processing on the screen using some 3x3 kernel or matrix, and you can apply whatever post-processing thing you want, just something that's interesting, something that shows that you can do it, okay? And you only need to work in this GLSL shader. Okay, that's for your lab. Hopefully everybody is otherwise doing well, wrapping up the homework and so on, and then we're going to move on to the exciting world of ray tracers next. So I'm super excited for that. We're going to have a lot of fun and continue learning a lot of stuff. Okay, bye for now, and we'll talk to you in office hours, Piazza, and email.